Hello, everybody. My name is Craig Yanetsky. I'm a PhD student at the University of Cologne. We are setting up the astronomy on tap in Cologne. We want to set up astronomy on tap. So what we want to do is just try to engage the public and tell them a little bit about astronomy. Normally we would have this event in a bar, but we can't do that at the moment. So joining with me today is the rest of the committee. Maybe Alina, you could start.
Hi all, my name is Alina and I'm a doctoral candidate at the University of Cologne. Brand? You are muted.
Yep, there we go. I'm Brand Gacious. I am a postdoc at the University of Cologne.
Hi, I'm Veena. I'm a Humboldt Fellow at University of Cologne.
So we are joined today by our very special guest, Dr. Volker Ossenkopf-Okada. He is a researcher at the University of Cologne and an expert in the observation and physics of the interstellar medium. Volker, hello. You can start your presentation now if you want.
Okay.
Looking forward to it.
Thank you. So then, welcome to some presentation about great astronomy in the air. And to start, I have to ask you to fasten your seatbelts and put your seat back into upright position, because now we are going to take off. We are taking off here in a very special plane. Actually, when you look into the plane, there are not that many seats inside, but you will find it's full of computers and operators, and all they are focused on the output of this instrument that you there see at the very back of the airplane. So this blue part with the instrument sitting in front of it. And they just watch what's going on, but to see what's going on, we have to think of what we want to know at the end. So what is it, what we are actually after? And well, what is astronomy about? It's about the sky, basically. And if you look at the sky, you see in the evening sky, in the winter here, the constellation of Orion, so a lot of stars. And at the end, it's standing there and you see nothing than just stars and nothing in particular. But 500 years ago, some guy had the idea to build some magnifying device, namely a telescope. And here is the telescope by Galileo Galilei shown. And if you take a telescope like this and look on the constellation of Orion, then things look different. So you can zoom in to some degree, and what you see there is that it's not just stars, but that you have some nebulous patches in there. So there is more than just stars. So all those nebula, so that makes just bigger telescope. So that's a telescope that we have here in our house for student education. And if you have a telescope like this, which is a diameter of about 12 centimeters, then you can already look deeper into these nebula and further zoom in, and it clearly becomes interesting because now the nebula itself becomes visible with some structure. So it's breaking up. It's not just a patch on the sky, but you see here some shape in the nebula. So you have some flame-like shape. And of course, that makes us even more curious. So ways to build even bigger telescopes. That's what is currently available. So here on the top, you see an 8-meter mirror being built. This is then integrated into this big structure here on the bottom. And this is a telescope of the Very Large Telescope, VLT, that is built by ISO on Paranal in Chile. Actually, they built even 4 out of those. They are shown here. So this is the configuration on Paranal. And if you have really such a huge telescope of 8 meters, then we zoom in from the VLT, where we find more and more structure here when really going to an 8 meters telescope. So that makes us, of course, way more curious what we see there. And one way is to ask for an always bigger telescope. And one of the plans here is a 40-meter telescope, so 5 times bigger than the VLT that I just demonstrated, that is planned by ISO in Chile. But at the end, what you get there is only sharper and sharper pictures. That does not necessarily help you to learn what is really going on. And that's why we try to use an alternative solution. In principle, of course, we would also have a big telescope. But what we are going to do is look at this jumbo jet here, which is up to scale here next to the ELT, which of course can only house a small telescope, but which has a major advantage compared to those huge telescopes. And the background of that advantage is physics that was actually discovered by William Herschel in the 18th century. So what he did is a relatively simple experiment that most of you have done to some degree at school. So just take a slit and put some sunlight through it, and then a nice prism behind that slit. And what you see is a rainbow behind it, so the nice splitting of colors. So you see the violet, green, yellow, red. And so that experiment of splitting light into the different colors was known at the time. And what he did at some point is he just forgot the thermometer next to the screen on the desk. And what he noticed is that for some reason, the thermometer got hot. So it showed suddenly a higher temperature. And what he concluded is that there must be radiation that is not just the light that we see here in the colors in the rainbow, but there must be some radiation that represents heat. So this gives us a completely new view on the universe if we think of the possibility of heat radiation. And to demonstrate this, I show you here my picture in terms of heat radiation. So you see me now talking, and of course it's quite a different picture compared to the camera that I showed you before. So you see the cold microphone. You see, well, my nose is a bit colder. Oh, the fingers are very cold. And my head is, of course, warm. So compared to the picture that you had before, this is quite different. Can I switch on my camera as well? Let me see how I can switch on the camera. Oh no, video should be on. Sorry, then that was an error from my side. So you see my picture and you see my infrared picture. And that means you have now a completely different impression from me. So without this infrared picture, you basically don't know how I'm heated up. So this gives a lot of information. But there is one problem with this. Namely, I have here a small experiment. What I show you here is, this is just a glass shield. So through the normal camera, you still can see me, but through the glass shield, you can't see me at all. So yeah, that means because of the water, we are actually in a glass house. So namely, this you all know from the discussion about Earth warming or climate warming, namely that we have the atmosphere which contains a lot of greenhouse gases, and actually the main greenhouse gas is water. In terms of the total contribution, CO2 is only the second. And that means what you see here is the sun coming from the light coming from the sun being partially reflected in clouds, but a lot of that arriving on the surface of the Earth and then warming up the Earth, and the Earth radiating away heat radiation. And because of the greenhouse gases, in particular water and CO2, not all infrared radiation can get out, but most actually is not getting out, which of course means if no infrared radiation gets out, there can also be no infrared radiation coming in. So at the end, we have no chance to make these infrared experiment that I did here in terms of astronomy when looking through the whole Earth atmosphere, but it means we are to some degree blocked by this layer, and the only way there to get forward is to get above the layer, and that is now the reason that we go into the air. So what we have here is SOFIA, the stratospheric observatory for far infrared astronomy, or for infrared astronomy, and what you have here is a 2.7 meter telescope. So this is already quite big. So of course we want to be as big as possible, but it's just the biggest telescope that we could put into an airplane. And with that now being above most of the water, namely in about 14 kilometers altitude, we can observe infrared radiation from the sky and get the information. Here we have a quick look into the plane. So what do we have here? So what you have seen in the beginning was the camera being here, so next to all those control computers. And what we could see at the end of the airplane was there this blue shield and an instrument sitting here. And what we could not see inside the plane is namely what looks out of this window from the plane, which is this 2.7 meters telescope that is then hanging or outside, so looking into the atmosphere above the water. And well, you see there are, of course, more things in here. So sometimes there is education personnel flying with them. What is not shown is here the crew that flies the airplane and so on. What do we actually see here? Oops, wait, this is too much. What do we see when we look in the infrared? And an experiment is nicely shown here. So that is taken with the infrared camera, and looking at that blob, you can guess what it is. So we observe gases, and obviously the gases in this case are not that smelly, but that also contains some water vapor and other gases. So what we want to know, of course, is more in detail, what are those gases that we can see in the infrared? And for this, we can employ some spectroscopy, namely the knowledge that all the gases radiate at specific frequencies. So they are special kinds of radios. This is shown here for an example, for a flame, that if you look at this burning flame, even in optical wavelengths, you see that there are individual lines in a spectrum. So they correspond to particular frequencies. So this is shown here for hydrogen and helium, but you can do this for all possible materials that you have in the gas, of course, also for the water vapor or CO2 or whatever. So if you measure through all those frequencies, you get the composition of the gas. So that's the fully new dimension that you cannot just get from the normal telescope, that we get this full composition of the gas. But of course, we have to measure all those frequencies. So what we need is a kind of radio receiver in the infrared. Problems in that. First of all, is the antenna size must about match the wavelengths. And if we are in the infrared wavelengths, we talk about sizes of less than 100 micrometer. So you have to build such an antenna with less than 100 micrometer. That's far from trivial. Then we measure heat radiation. And of course, that means the receiver should not radiate more than we measure. So the receiver must be very cold, and we count this in terms of Kelvin. So well, temperatures of minus 260 degrees centigrade, so very low temperatures. And furthermore, the frequencies that we receive cannot be directly amplified. So we are here in terahertz frequencies. What we can amplify directly are some 100 megahertz or gigahertz. So we need some special technique. And the solution to this is GREAT, which is this receiver, the German receiver for astronomy at terahertz frequency. That's what the abbreviation is for. And that is actually an instrument that we built here in Cologne together with colleagues from the Institute for Radio Astronomy 1. And the amazing thing is there, what you see at the bottom is the antenna. So there we have structures that are partially smaller than 2 micrometers, but the whole instrument fills basically all the space at the bulkhead of the airplane. So a huge instrument there that should be moving. And what we then find, if we really look at this instrument, are a lot of quasi radio stations. So we see all those lines in the interstellar medium that come from different kinds of gases. And you see some of those lines here have names on them. So they are identified: water, carbon monoxide, sulfur dioxide, methanol, acrylonitrile, and so on. So we have really a huge lot of different gases. that are there, all visible if we can make it to the airplane and use our great receiver. And for each of those gases, then we get a distribution on the sky. Here is the example for our Orion Nebula that we have the picture that you saw before in the visible light, and on the right-hand side, you see the same area in the irradiation of ionized carbon. You see there are similarities, so you see this kind of flame structure there that is visible in the optical and in this ionized medium, but you see, for instance, here in the upper part, the structure looks completely different. So what is dark here is bright here. So we have completely different information. But there's even more than just getting all the different gases on the sky. Namely, what we have on top of that is an effect that is based on something that you know from the Earth. This is the so-called Doppler effect. So if you have some moving sender, the frequency that you hear differs from the original frequency. So if we have here the experiment of this car moving towards us, what you hear is something like no. Well, maybe we can do it like this. So while the car is moving towards us, you hear it at a much higher frequency than the original honking. And when it's moving away from us, it is at a lower frequency. So what we can do in this way is look at exactly the frequency that we see from the different lines and compare them with the frequencies that we know from this material on Earth, and then compute what is the velocity that the material can actually have. So that means we do not only get now the picture of the sky in the different molecules, but we get really their motion. And this gives us, of course, now a new dimension. That is shown here on the right-hand side, where we go through this ionized carbon and now look at different velocities. And you see at each velocity, you give a different shape of our Orion Nebula. So we go from a material that was moving towards us to material that is moving away from us. And on the left-hand side, you see the same again in 3 colors. So blue is material that is moving towards us. Green is material that is relatively at rest, and red is material that is moving away from us. So what we have from this is now not only a picture like you would get in the optical, but we really get also the dynamics. And what we want to do with that at the end is really see from that dynamics how the gas is moving and how it's making new stars. So a process like the one shown here, where this is a numerical simulation how stars could form, and this takes millions of years. So of course we cannot wait for millions of years, but we can look at the velocity of the gas. Does it fit to such a model of the star formation, and can we really learn how stars form and interact with their medium just from now having the full velocity of all the species of the gas, so having much more information than you could just have from the high resolution optical picture. And with this, I can try to bring you back to the Earth. And we are back on the ground. And now I'm open for your questions.
Wonderful talk. Thank you so much for giving it. We have one question from YouTube. That was, how do you know which line corresponds to which chemical?
Yeah, that's actually not so trivial to find out this assignment, and that's why we have here a large group in the lab of the First Physics Institute in Cologne that really tries to measure all those lines in the lab. So what they do is take those gases and put them into some long gas cell and try to get those spectra in the lab. Of course, if one knows the structure of the molecule, one can also try to compute this, but this is very difficult to theoretically compute. So what is usually done is they try to measure something like 20 of the lines of one molecule in the lab and then make a model that may cover frequencies that have not been measured in the lab yet. So this is quite a difficult task to really get all those lines. And we have some easy molecules here. Carbon monoxide is an easy one. There we know the frequencies all very well. But we have, for instance, also detected complex molecules like alcohols or ethanol, where we don't know all the frequencies well enough yet, but there are many transitions so that we have already enough that we are sure that it was alcohol, but not for all of them we fully understand the physics yet. So this is ongoing research.
Okay. Another question we have is, how long does it take for the telescope to observe, or how long can it observe without burning out from too much radiation?
Too much radiation is not a problem at all. Unless we would look into the sun, then we would immediately evaporate the instrument. That's definitely something we do not want to do. But the radiation that we get from the sky is weak, so we can observe as long as we want. However, we are limited by being on the sky, on the plane. And of course, we have to land at some point. And usually we operate the airplane from Palmdale in California and have to go back to this. So at the end, you always look with the telescope from the left-hand side of the airplane. So you can only go in one direction for, say, half the flight. And the typical flight time is maybe 10 hours. So you can practically not observe longer than 5 hours, because then you have to go back to Palmdale for landing. So what we usually do is combine several sources that we have on the way, one source, on the way back another source, and maybe some other sources interdispersed as well. So that gives some very complicated flight track at the end.
Okay. Another question we have is, will heating up from the radiation affect your observations? Does heating up the telescope from observing affect the observations?
No, because we really have relatively little radiation from the sky. So if you look at the heat that we see in each of those lines, this is typically, say, 100 times colder than what we would see from the moon. And the moon is obviously not very hot. So to give you an idea, the radiation that we see from the sky is not really heating up our telescope enough. And at the end, the photons that we get are, of course, at best not absorbed by the telescope, but reflected by the telescope into the instrument, and the instrument is always actively cooled. So, of course, that's the point, that we have to have all the time some active cooling, that the instrument as such doesn't warm up and stays at those temperatures of, so just a few kelvins or a few degrees above the absolute zero.
Okay. We have a question actually about the spectrum you're showing right now. The comment was that the actual spectrum should have some noise. So what steps are taken to get rid of the noise?
It's correct that the spectrum has noise, and the noise in this example is actually so weak that you hardly see it by eye. So it's just the width of the line down here that is due to noise. So basically everything that you see here as a spike is a real detection. So this example here was a really long-term integration, so that the noise was at the end very small. If you integrate only for a short time, then of course you have a more noise, but by having a long-term integration, you get much less noise compared to the signal that you get from the sky. So that is our limitation in terms of the time. That's why we want to observe long, because that's the way to beat down the noise.
Okay. I think I don't see any more questions on YouTube. Does anybody in our committee have any questions to ask?
Yeah, I have one. So what's kind of the most exciting or interesting observation that you are hoping to be able to do with GREAT?
Actually, the observation that I showed here, or even this velocity resolved one that I showed before, so this type of observation to me is really the most exciting. So we have here an observation of this region in Orion where we really now see the velocity structure, and this gives us work for a few more years to fully understand it. What I want to have is the same kind of observation in regions where we know that stars are just forming. So the point here in Orion is there already a lot of new young stars have formed. So they have changed the structure of the region. So this is a very messy region. But I have regions on the sky like Taurus where I would like to have the same kind of observation, and to really compare the velocity structures in the different regions would make a lot of new answers on how star formation can go on.
Okay, great, thank you.
Yeah. I think think that's all the questions that we have. Thank you for the presentation. It was very interesting.
Okay.
I enjoyed the infrared camera section. It was very nice to see.
Yeah, thank you for listening in and sorry for the many interruptions.
It happens.
Hopefully I will get a new notebook soon so that then the problems wouldn't happen anymore.
No worries. A few people stuck around with us, so that's good. And I think they learned something. That's always nice.